Hello, welcome back to the meetup. Today we're going to cover creating data pipelines using AWS. We're going to get into creating data lakes and data warehouses. So welcome back and thanks for joining us again. Let's jump over to the slide deck. So just to cover the agenda a little briefly, first we're going to start out with the intro of myself, then we'll get into overview of why we want to get into data pipelines and event streaming, specifically why that is superior to batch processing. Then we'll get over into a review of part one of the AWS data pipeline series. Then we'll take a look at the new components that we're bringing into play here, namely Glue, Redshift, Spectrum, Elasticsearch, and Athena. Then we'll take a look at some of the components in the AWS console. We'll take a look at a demo, data processing demo, and a couple use cases, 3 use cases around various ways to utilize the data that we put into our data lake and or data warehouse. We'll take a look at the infrastructure as code that was used to instantiate the components. Brief news and notes wanted to cover with the crew, and then jump into any Q&A that may come up throughout the presentation. So let's just go ahead and get into it. So I am Kevin Tin, Cloud Application Architect Practice Lead at Worldwide Technology. Been in the industry for quite a while. Started out with software development, .NET, VB.NET. Jumped over into the Java virtual machine in Scala as my primary language there, and worked in several JavaScript frameworks, mainly doing front-end work, a little bit of Node.js, but I wouldn't call myself an expert there for sure. Then got pretty heavily into data streaming and data streaming architectures. Done a lot of work around Kafka, Kinesis, and event hubs. And additionally, I got into application architecture, predominantly within the cloud, within AWS, obviously, Azure as well, and hybrid on-prem solutions. Prior to quarantine, was an incessant traveler. Recently moved to Denver, fairly recently, probably the last 2.5 years. So a newfound skiing addiction is taking up any money that I'm earning. And then prior to Denver, I was in St. Louis and grew up in East Tennessee. So just a little bit of info around where to find information for this presentation. We've got the link on the meetup, as well as a couple links here into GitHub, etc. So if you haven't joined the meetup and you're just viewing on YouTube, please come join. We usually present once or twice a month, depending on really our schedules and kind of just the participation we're getting with the meetup. So diving into the meat of this. So let's do a little bit of an overview of part one, and I'll be in the slides for a while, so I'm going to go ahead and make this full screen, I think. Okay, so the goal in general is with these data pipelines, we really want to move away from batch processing, getting large sets of data on a schedule, and really moving into event-based processing, which is more so, let's go ahead and process data as it comes in from analog or real-world events. And so to demonstrate, kind of like how the architecture scales out, in a batch-based environment versus an event-based environment, we'll start out with a simple example of just a couple applications and a couple databases. And so here you see it's very common, kind of pre-microservices, if you will, for application to have an API. There's dependencies between applications. So one API may be calling the data source or the persistence layer of another API, etc. And then there's batch ETL, sometimes in between applications and sometimes in between the data warehouse. So while this seems pretty reasonable, as you fan this out to just 4 applications, it really just starts to get pretty ridiculous. And so enter the data pipeline and microservices and some principles around kind of protecting the data. One application has its own database. No other application can touch that operational data store. However, in real time, using change data capture, etc., from that operational data store, data events are emitted out to the data platform, and then in real time they can be emitted out to another application or a data warehouse or data lake for analytics or just long-term storage, if you will. So reviewing the for application use case, it's pretty obvious that this is a little bit more simple to maintain, understand, etc. And so that's really where we're going with this is, you know, hey, how do we start moving towards this data platform, these data pipelines, etc. And so going back to part one, we use Pulumi to create the infrastructure as code. I have another repository out there if you want to beef up on that. For this particular series, I wanted to use Pulumi because I wanted to test out their C# support. We're also big fans of Terraform as well, so don't take that as a slight to Terraform. Really just wanted to kind of kick the tires on the 2.0 release of Pulumi. So I would say very good job to them. I found it to be a pretty good experience overall. And so to review kind of the use cases, problem statement, etc. around part one of this is we wanted to kind of emulate an Internet of Things use case where we produce messages for sensors. And you can think of these as sensors at a manufacturing site. And so we're going to key in on temperature and pressure readings because these are pretty key to the safety of a manufacturing site. So this is a pretty common use case to monitor this type of data. And so once the raw messages come in, the raw data from the messages as they come in the native form from the sensors, we're going to go ahead and just store that as is for compliance purposes. Pretty common tactic in data lake and data warehousing. And so at that point, we'll go ahead and start separating out the messages, one for temp and one for pressure. With the pressure data, we'll go ahead and enrich that with the altitude. That seems like something that could affect the pressure reading. And with the temperature data, we'll go ahead and enrich that with the ambient weather reference data, the temperature of the manufacturing site at the time, because that could influence the temperature within a manufacturing process. If it's 110 degrees outside, may not be a good thing. We don't know, but we're going to go ahead and join that. Down the road, may take a look at that with some machine learning and see if that's actually the case. But we wouldn't even be able to test our hypothesis if we didn't enrich that data and then source it into another location. And so, with that being the case, we also stored the enriched data into S3 data lake and put Athena on top of that for kind of data science type of query activities. And so, where we ended up with that, to draw a picture, was the sensor producer sending into a data stream. We store our raw data for compliance purposes. We split on the sensor data type, pressure or temperature. Then we go ahead and enrich that with reference data for the type of data that each stream is dealing with. And then we go ahead and send that out to a Firehose Delivery Stream, which is a very easy way, a no-code way to send data out to other data sources off of a stream or a Stream Analytics application. And then from there, we put that into S3 buckets, data buckets, apply Athena to that so we can query it. So within that, we create a pressure table and a temperature table. And then finally, we had the Athena results database, which is just kind of an internal component of Athena and how it works. And so for anyone that didn't make part one, we can take a quick look at the components that we use there. So the Kinesis Data Streams, massively scalable, offers a pub-sub sort of streaming technology so that you can have multiple sensors inputting into a data stream, for example, and then multiple processes reading and maybe monitoring for anomalies and hopefully trying to prevent some sort of issue, save money or be more safe, etc. And so with that being the case, going down into the Firehose, and so this is a managed service for delivering data to those output destinations. So at this point, you're talking about S3, Elasticsearch, Redshift, and I believe Splunk is the fourth. And so, like I said, no code to send your data to another source, live to fight another day. Spend your time on the hard stuff, not the easy stuff. And so with that being the case, we get into data analytics within Kinesis. And so that gives us a service to transform, enrich, analyze streaming data, and it's all done. You got a couple options, but the most popular is by far the SQL syntax. So people that are familiar with relational databases can very easily get in and manipulate and enrich stream data. And so definitely a very popular service, very powerful as well. And so we moved down to S3, and so this is Simple Storage Service, one of the original AWS services. And so this is just blob service, or blob storage. So you think about wanting to store a JSON or a picture, text information, really across the board. Supports really most use cases. Extremely scalable, depending on the tier of storage you use, gets very cheap. Really one of AWS's most popular services, and it's really pretty impossible to do too much in the data pipeline realm without using S3 at some point. So definitely, if you're not familiar with that, I would definitely look into it. And then finally in part 1, Athena, we use that to query S3 data, and so that gives us like kind of a data science, data lake, data exploration tool to go and look at that data that we've collected or enriched. Just a lot of use cases there in general. And so with all that being said, let's move into part 2, what we're going to get into today. And so I realize this is a lot, so I'll try to summarize in a succinct way. So we had problems with Athena last time where it only returned a single result. So we're going to go ahead and fix that. We're going to do that by using a specific file format. Then we're going to go ahead and load the enriched data into Elasticsearch. A typical use case here is applications need to get at data very quickly and also need to do full text queries. And so with that being the case, Elasticsearch is a pretty great tool, and it's supported in a no-code way. And so going on to the next use case, we're going to get into the analytics, and we're going to get into the streaming and enrichment, etc. We covered this a little bit. Then S3 as well, and Athena, of course. And so looking into the architecture here, we can see that it's really kind of, I don't know, exploded might be a word, but I think it's worth noting that it's not quite as complicated as it seems, whereas off of each pressure or each sensor type enriched stream, we're outputting to 3 sources now. So we were already going out to the S3 bucket with Athena. What's changed there is we're going to use Glue to do the conversion between a JSON message to a Parquet formatted message, which works exceedingly well with Athena versus a raw JSON stream. There's some quirks there. You have to do formatting, turn it into a JSON array, and it's really, in my opinion, just not worth it. And also you save some money with the Parquet format as it compresses down pretty nicely. So we'll actually take a look at that. It's pretty cool in my opinion. So we're already doing that, so we've modified that just a touch. We're going to go ahead and stick records out in Elasticsearch off of our enriched streams. And so that represents this Firehose. And the final off of each enriched stream is we are going to go into Amazon Redshift for enterprise level data warehousing. And so it looks like it's exploded quite a bit, but really we've added a few services in Glue, Elasticsearch, and Redshift, and really just expanded out to support all of the various services. And so the components. So if you're not familiar with these components, we like to dive into them just to, our main goal here is really to educate. And so in case you've not heard of Glue, it's a fully managed ETL tool. Allows you to transform, enrich your data, take it from one source to another. We're using it, as I mentioned, to transform to Parquet in our enriched Firehoses. Other very common features are data catalog. We're using that, but kind of indirectly in my examples. Schema detection, so you can put a bunch of data in a bucket, and it'll go and figure out what the schema of your data is, which is incredibly powerful. From that schema detection, it can get into code generation. So it allows you to pretty easily specify in the console, something like that I want to take this field and I want to convert it, say it's a string, and I want to convert it to an integer, and then I want to store it in a field that has a different name. And so at that point, it can do that code generation and really kind of lighten the load on the more of the kind of repetitive sort of tasks that get into ETL work, because Lord knows ETL work is filled with a bunch of repetitive tasks. So that's a really nice feature. Additionally, provides data cleansing. And so with that, you can ensure you have a certain data type in a field, null it out if the data does not conform to your expectations. Just a lot of possibilities there in general. Job scheduling. So if you want to get into that sort of like every 4 hours we pick up this batch of data, we transform it, and we put it over here for these users. You can certainly do that, and it's a pretty good tool for that. And then also streaming ETL. So as messages go through a Kinesis stream, we can use Glue to specify the transformation. So that's definitely where we're at. So getting into the other components, Elasticsearch, fully managed search service, specializes in full text searching. Think about a search engine, if you will. And so with that being the case, it's built on very established technology in Apache Lucene, and so provides that full text search service. And from Wikipedia, there's a kind of a nice overview of Lucene here. I won't read that to you. And I think it's important to note with AWS, you get a managed version of that. And so a lot of the overhead of knowing how to run a cluster is gone, but it is a dedicated cluster and it constantly incurs costs. So that's certainly something to keep in mind as you start thinking about and considering using that in your projects, recommending it to customers, etc. So getting into Redshift. Redshift is Amazon's data warehouse, provides columnar storage, which provides very good performance, industry-leading performance depending on the metrics you're tracking. Very efficient storage, massively scalable up to petabyte scale storage and analytics, extremely powerful. Price is pretty good. Price is actually really good for it. Like I said, extremely performant queries using columnar storage, and we'll get into what that means a little bit later. And additionally, similar to Elasticsearch, you've got this managed cluster. So a lot of the headache is, pretty much taken away if you're willing to pay for it. And so that being the case, if you want to spin up Redshift and play with it, I'd recommend spinning it down overnight. It's pretty expensive. Unless you're doing, production or enterprise level development with it, you may not want to eat those costs. And so it is cost competitive, but you have to pay to play. And so getting into columnar storage, it's a pretty interesting concept, kind of heady, honestly. So if you were to look at traditional row-based storage, on row 1, you would have the US country, alpha product, and sales. And so, very predictable stuff. So that results in this row-based storage kind of paradigm where you think about it, one row, kind of like Excel. So if you shift into columnar storage, you've got information starting to be grouped together based on the individual columns. So at this point, if you wanted to run some analytics and figure out, say, which product is selling the best, analyzing the columns of product and sales together, that would lead you to that answer. And with like very large data sets, the row-based storage, that starts to become inefficient. So with columnar storage, you really get the ability to compare data a little bit better. You get better analytics. You also get a much smaller footprint on the actual physical hard drive, which results in cost savings. And so as you start to get into enterprise level, petabyte level data warehousing, this becomes extremely important. So a little bit of an aside there. But I think at this point, let's go ahead and get into the last one. And so Redshift Spectrum allows you to connect your Redshift cluster into external data sources. We're going to use it with S3. And so with that being the case, the pledge that Amazon gives is this allows customers to build out exabyte scale data warehouses that you pay for the queries at the time that you use them and in the number that you use those queries in. And so at that point, you kind of got the pay to play, buy by the drink kind of model, however you want to phrase it. But I think a big takeaway here at the bottom is it's really pretty staggering to look at what exactly is an exabyte. 1 billion gigabytes. Kind of blows my mind, but that's where we're at. And so with all that being the case, let's go ahead and jump into the console itself and get into the process of building out this architecture. Speaking of the architecture, let's go ahead and jump back to the picture of it just to keep that fresh in everyone's head. And here we are. So the first thing we're going to do is we're going to look at what was required to create these glue schemas to be able to convert the Firehose data into Parquet, which works better with Athena. And so with that being the case, we get into, let me kill this out. Let's go ahead and just jump into the console itself. So navigate to Glue. And within here, we've got a couple of temps here, but we've got a pressure table here. And so at that point, we can go in and we have basically defined the schema, including these columns. And so I think also important here is we're talking about the input format being Parquet, etc. So let's go ahead and look at, just kind of dive into the code, what we did to create these Glue schema tables. And so with that being the case, we create a catalog table, which is basically describing a schema in our particular case. And we're going to go ahead and tell it that we want to do some compression, and then it's an external table that can be queried by other services, etc. Specify an input format of JSON and the output format of Parquet. If you remember from part 1, we couldn't really query with Athena the S3 buckets and get all of the results because like the JSON data, the text data was just coming out in a continuous stream. There weren't line breaks. There was not proper array notation. All sorts of problems that would make all sorts of issues that would cause problems if you're trying to query JSON. And so with that being the case, we went ahead and specified that we're going to go ahead and basically have this transform from JSON to Parquet. And so if we get back into the place where we call this method from, important to note that we are also specifying, and so here, and I'll zoom in, is where we are actually calling this create glue table. So we're passing in the individual fields that we're going to be using from each one. And so with that being the case, let's go ahead and jump back into the Kinesis Stream Analytics Applications and just take a look at one of these kind of in action. And so we'll get down into the real-time analytics, and here you can see this is where I was talking about you can start to use a SQL-like query to get data off of a topic. Really pretty powerful here. And so before we get into actually pumping some data through here, we can see this reference data. So site ID 1, the altitude's about a mile high. Site ID 8, we're about 20 feet from sea level, so on and so forth. And so let's go ahead and just jump into producing some data. And so with that being the case, I've got a Python application that just goes ahead and pumps data onto the Kinesis stream. And so we'll just let that kind of roll. And now you're starting to see this data come in through the stream and then be enriched with this altitude data. And so with that being the case, we can jump into S3, and let me see here. I'm going to refer back to the diagram as this is not simple, I would agree. And so we jump in here, and really what are we talking about doing? So we've got this glue schema for temperature, pressure, and then we go ahead and apply that with the fire hose, and it goes into this bucket here. So let's go ahead and take a look. Looks like I have my buckets backwards. First time I've done this slide deck, so I need to make some notes for typos, etc. Speaking of, if you see any typos or have any questions, just drop a note on the live stream chat. We certainly appreciate that, and we love the interaction, especially doing these remotely. The interaction, it's pretty nice, So let's go ahead and jump into S3 here, and then take a look at the enriched data. And so let's go back here. I feel like I'm in the wrong place. So we'll get into here, and just to take a look at this Parquet format, for the people that were here for the last one, we would get into this file once we dig down through all of the various timestamp type folders. We got here, we saw a format that we could read. We saw a JSON stream that was basically input into here. So actually, let me download this. Save this, come back here, let's open this up. I would say pretty firmly that for stuff like this, I'm a Sublime fan. But any old text editor will do. And you start to look at this and you say, well, what in the world is this? So we've now converted into this columnar-based storage. We've also compressed it using Snappy, and we're not storing just plain text. So this is no longer really usable for a human. And so it's like, well, at that point, how do we get at this data? You know, like we're storing it, we've got queries we need to do. I've got data scientists that need to use the data in this bucket to do exploratory type of queries and figure out how to build models, just, you know, the whole gambit of use cases. So getting back into the console, that is what we wanted to do with Athena. And so I've kind of created this beforehand, as I think there's a lot of content, so I wanted to go ahead and get everything up and running, make sure it works, etc. But to dive into the creation of a table here so that we can query an S3 bucket. Pretty simple. We stood up the Athena database with Pulumi, the coded infrastructure. I think it's worth noting creating these tables. I have not found a way to do that from the coded infrastructure, so I've had to do it manually, for better or worse. And so get into the Athena database, and we'll call this maybe temperature. And then it wants the location of the data. So if that being the case, go back over here, and the output of the Pulumi up resulted in some output variables, and so we'll go to the enriched temperature bucket here. And so creating this table is as easy as doing that. Difference from last time, instead of JSON, we are Parquet. Once that occurs, we need to start defining some columns just for the query. That glue schema that we created earlier was used for the transformation, but I haven't found a way to hook these tables into that. There may be, may not be. If you know it, drop it on the chat. We'd love to hear. So let's jump into some of the queries that I've got created here. And so when you create the bulk columns, it's just simply a comma-separated list of column name and data type. Interesting to note, in Athena, they have a data type string as opposed to varchar, if you're familiar with SQL data types, so I thought that was pretty interesting. And so go ahead and do that. Not going to create a partition. That's a little advanced for this talk, so creation of the table occurs, and so it will generate this query. If you wanted to create these tables as part of a CI/CD pipeline, I would recommend crafting these queries yourself and running them as a part of your infrastructure CI/CD pipeline. That's how I would get around the limitation within Terraform Bridge and subsequently then Pulumi around creating these tables, or at least to my knowledge, the lack of that support. So we've got the table. So coming out here at this point, we want to go ahead and say, well, give me all of the information from one of these tables we created. If you remember last time, we'd get, oh yeah, I forgot SQL. Pray for me. So if you remember last time, we'd get basically one row. And so now we've got the full data set at our disposal, very important. So now your data scientists can get in, start messing around, looking at this data, trying to explore, figure out trends and patterns, build their models, etc. Full support for the SQL query syntax. So we're interested in, say, like site number 10. Go ahead and get into that. And then we can go ahead and just start getting at the data however we like to. Again, pretty standard SQL syntax here. So once you get it in place, it's really pretty intuitive for your users to pick up, provided they kind of come from that world. So with that being the case, let's go ahead and start looking at Elasticsearch. And so I think it's probably worth looking at the various fire hoses at this point. We go back to the diagram. And so from an enriched stream, we've already looked at this S3 production from the stream using Firehose and transform using AWS Glue. And so from there, let's go ahead and start looking at the pressure Firehose that's going to feed our Elasticsearch service. And so pretty simple, honestly. And so let's take a look at these. So we've got a couple. I've put the suffix ES on these just to know that they're going out to Elasticsearch. So in the context of the pressure readings that we split off and enriched with altitude, we can dig in here. And so we are coming from a source of the enriched pressure data stream. We do not have data transformation enabled. I think it's worth noting that data transformation is specific to having a lambda that runs on every message. If you're doing that glue-based conversion that we use to get the Parquet format in our S3 buckets that we are querying with Athena, that doesn't show up on this dashboard, so I found that to be a little confusing, to be honest with you. And then finally, the destination. And so we're going out to the Elasticsearch service, and it's going to go out to the meetup search domain. Domain is a term that exists within Elasticsearch. And so I think of it kind of like as the Elasticsearch instance. I'm sure that's not the most academic way to think about it, but it works for me. So with all that being said, let's go ahead and jump into Elasticsearch. And so here we've got that meetup search domain. And so from each one of these enriched streams, which have the Firehose delivery stream going out to Elasticsearch, those are going to go to an index. And so an Elasticsearch domain can have multiple indexes or indices in it. And then from there, you can query each of the indices as you see fit. And so with that being the case, here we can see, ran this a couple times. So here we go. And so with that being the case, got a little duplication here. Interesting. Looks like that's based on, oh, yeah, so that's the date in GMT. So we crossed over into tomorrow over in London time, so it created a new index. Probably a little bit of a bug in my Pulumi code, but easily fixable. And for the purposes of the demo, I think this is probably acceptable. I think we'll get by. So with all that being said, here we can see kind of the proof, if you will, of our data being sent out to Elasticsearch. So we'll get into what it is that needs to be done to really get at that data. And so Elasticsearch doesn't really have much of a user interface, if you will, to get at the data in the console. It'd be really easy to argue that's exactly the opposite of the point. Like, Elasticsearch is not really meant for at the speed of the user clicking some buttons in the AWS console. Like, really, you're talking about hooking up your customer-facing applications where, you know, say they get some sort of abstract, some sort of summary of text. If they want to look up entries, think about storing the text of an entire book, for example. If I want to search for, you know, white whale or something like that, you know, if we're indexing books, you know, we end up coming back with like Moby Dick or something to that effect. So at that point, you have an application that your customer's interacting with, maybe inserts a couple or enters a few terms, and then at that point, it goes and programmatically hits. So this lack of interface, I think it's very justifiable to say the least. And so if we want to actually look at what happens to interface with it, let me get back into my console here. We can just go through an example of getting at Elasticsearch via curl. And so at this point, anything that can make a HTTP GET request can start to get at data in Elasticsearch. And so with that being the case, we've got the fully qualified name, and then we have the index, and then we have the operation that we want to complete against the index. So, and then I'm going to pipe it into JQ, as that's a very awesome command line utility to oh, one sec. Terminal's going crazy on me. Come back to me. So JQ will basically just, if you just pipe into JQ and take the root of the JSON object, it will go ahead and format it in a way that's easier to read. So we get here and we're starting to see information from site 11, site 10. So long and short of it is we've got information coming back for every entry in the index. And that's really not what you're going to do with, you start thinking about searching, etc. So if we wanted to, let's see, let's start from scratch with curl again. And so let me expand this just a little bit further. That's probably pretty hard to read. I'm actually just going to grab this and get it to the top. And so this is probably a little bit easier to read. And so here we're going to go ahead and do a get against the fully qualified domain name, the index name. We're going to hit the search service, and now we're actually going to pass in a query. And so our query is going to be site ID :3. So this is the syntax to go ahead and hit obviously an index. And so let's go ahead and do it and see what we get back. And so now at this point, every site that's coming back in the response is from site number 3. And this becomes more powerful when you start thinking about, well, if we're talking about pressure, we know that it shouldn't be above 200. So you could go and query for everything where, this text starts with a pattern of 20, for example, or 2, any number. And so if you convert this to an integer data type or a float double type data type, a numeric data type, you can start doing, quality operators, inequality operators, greater than, less than, stuff of that nature. So really pretty powerful tool to really kind of, I think, assist your users with searching for data. And the real use case here is large volumes of text. So again, kind of like a search engine. And so with that being the case, jumping back to the diagram, it seems like it'd be just a ton of work. Like we went ahead and sent this data out to an S3 bucket. Looks like the buckets are backwards. The first run with a new deck. I always like that. So with that being the case, why are we going to do all of this extra work to go ahead and send it out to Elasticsearch as well? Well, the good news is it's not a lot of work. So if the use case is there to support the cost of running Elasticsearch, if we want to go ahead and start looking at how much work was done to be able to support the S3 Firehose and the Elasticsearch Firehose, I think we can take a quick look at the code. So bear with me for a sec. And so let's see here. And so we get into this section here where we're creating our Firehose Delivery Streams. And so we create an S3 Firehose. I've got some code to create a Redshift Firehose. I'm not going to show that off too much though. And then also the Elasticsearch Firehose. Looks like my casing is off there just a touch. And so at this point, the code to create the Firehose out to Elasticsearch, you're looking at about a dozen lines of code. So this is where those coded infrastructure libraries and frameworks really start to pay off. If you're talking about Terraform, if you're talking about Pulumi, if you're talking about CloudFormation, all of these. Once you start to get these templates around creating a thing the second time is really quite easy. So I think of note here is this section here. So we're saying destination, Elasticsearch. Since we're going to Elasticsearch, we're going to have to give it configuration. So we're going to have to give it the domain that we're going to, that meetup search domain. It's going to have to go to an index name. And so with temperature, that index name is temperature with that date on it, and with pressure, it's pressure with the date on it. Certain versions of Elasticsearch require a type name so that it can start to kind of develop the concept of data entities and types. And so with that, I'm just using the index name as well. And so that, not a lot going on there. So we hop up to, if we want to create these enriched S3 fire hoses. That portion, and this is a little bit maybe more convoluted because we've got this transformation going on, but we simply set it to extended S3, tell it where it's going to go, what privileges it's going to be sent with. For conversions, we have to have a buffer size larger than 64. Fun fact, just leave it at that. Then we get into saying what is the input format, and this Hive JSON Serde is a deserializer, so this supports receiving data in JSON format. So then we go ahead and say the output is going to be in a format as well, and this is where we start to move that data into a Parquet format. So with that being the case, we finally need to give it a schema so that it knows how to format some of that Parquet information. Since it's basically a big long data stream, it needs to know where the delimiters are in the data stream between messages and fields, is my suspicion. Not an expert on Parquet, but I'm gonna throw that out there. And so really you're talking about, here we've got another, I don't know, 15, 20 lines of code that are different, so we're not really doing a ton of work to be able to get multiple outputs. And so I think it's really pretty powerful. And if you're not doing your data conversion, and maybe this is the example I should have shown, that Elasticsearch and Elasticsearch configuration becomes S3 and S3 configuration, and now it's 4 lines of code. So you're really not having to, bust out too much work to be able to define these different destinations. And so that being the case, jumping back to the picture, with just a little bit of extra work, we can now send this out to another destination. And we'll get into the code that created the Elasticsearch service here in a bit. And then finally, we have a Redshift Firehose. And so with that being the case, we can take a look at that just real briefly. So again, it looks like it's not really much different than the Elasticsearch or the S3. So pretty good stuff there. So the long and short of it is, with the 3 different destinations, we're not really having to do much work once we get it onto the stream. And so if we start to go back to our concepts that we're really trying to work away from or towards, depending on if you want to be half full or half empty, this convoluted mess of basically a communication mesh, you really start to point to this. And so at this point, coming off, say this is a data stream, you get a fire hose here, a fire hose here, a fire hose here. And so you're really starting to get the centralized point of data control, governance, etc., and work away from really the applications having to know too much about each other. So pretty good stuff. So jumping back down into the use cases, the next thing that we stood up for this demo is Redshift. And so we'll go ahead and take a look in here. Stood up a Redshift cluster. It's a single node cluster. So we can jump into here, take a look at some of the details. So from the dashboard, they give you pretty sweet metrics. Obviously, I'm not utilizing the cluster at all. So I think that's worth noting again, is Redshift is super high horsepower. So this sort of demo activity is really, we might be insulting it. It wants more work to do. So with all that being said, we can take a look at how do we go ahead and start to create these Redshift Spectrum external data sources, and how to join external data sources with internal data sources within Redshift. And if you recall, Redshift allows you to go out to your external data sources and bring that into Redshift, if you will. And then at that point, if you have tables that are internal to, if you have schemas tables internal to Redshift, and you've got schemas tables external to Redshift, and they have good foreign keys, you can start to join that data, which becomes extremely powerful. So with that being the case, let's go ahead and take a look at what is required to do that work. So back into Redshift, get into the editor here. Some instance types in Redshift, just as a kind of a hint. Allow you to use this editor inside of the console. Again, this is like Elasticsearch, console. Activity at the speed of the console is really kind of not really going to move the needle too much here. So in order to get external data accessible within Redshift, first we have to create a schema that represents the Spectrum data, if you will. And then secondly, we have to create the table which represents the external data source. So to get into that, here we go. There's Studio Code. Back into our queries. Let's get rid of that. And so, let's go ahead and start here. So, again, would recommend doing this within your infrastructure CI/CD pipeline. You can run these queries from a Jenkins job or something to that effect. Oh wait, we're at AWS Meetup. Put that stuff in code build. So with all that being said, jumping into the actual query itself. So here, pretty important. Let me zoom in. I'm sure this is incredibly difficult to read at that size. We're going to go ahead and create a schema, and it's going to be defined as external. And so this is a schema for tables that are going to live outside of Redshift. And so we've got from data catalog. Data catalog is a portion of Glue. So once you start getting into this, you start utilizing that Glue data catalog. Then we're going to go ahead and name the database. I have arbitrarily named it Spectrum DB. You will have to provide the IAM role that has the ability to both get into Glue and also into S3. When possible, don't share your account ID. Once upon a time, that was in there for real, and I went ahead and created the schema and table. So just trust me on that one, please. I'm going to specify the region we're going into. I always like to be super explicit with stuff like region. I don't like it when I get surprised and stuff's not where I expect to find it. And then finally, this database, Spectrum DB, if it does not exist, we're going to go ahead and create that. And again, that's external. So we are doing pretty interesting things with Redshift here, where we've got entities that can be queried from within Redshift, but the storage is entirely in S3. And so how do we get into that? Once we have the schema, we need to go ahead and create a table to query. And so with that being the case, I'm going to go ahead and grab this snippet. And so let's take a look at what we're doing here. And actually, for reference, I'm going to grab just a touch more. So, as you may recall, we created this Spectrum schema here. And so, we've got the Spectrum database as well, which is keeping the schema information. And so with that being the case, we're going to go ahead and create an external table in the Spectrum schema, which, if you think about old school SQL, the standard schema may have been something like DBO. We're getting wild and crazy in the cloud, so I'm going to go Spectrum schema here. And we're going to call this table pressure. And so this is going to have our pressure readings. And so the same 4 columns that we saw earlier, site ID, the reading value, the timestamp, as well as the altitude, all very loosely typed. Pay no attention to that. We're going to specify the data are stored in their location as Parquet format, and so that's possible from that Glue transformation that we did. And then finally, we'll go ahead and specify the location. And so with that being the case, we've created a table, and that table resides within a schema that we've created. And so at this point, this probably isn't really much more than, really what we get out of Athena at this point. Basically, we're querying things from an S3 bucket. Like, well, hey, that's what we did with Athena, so what's really going on here? So go ahead and run this. Waiting for it to get queued up. Again, it's a single node cluster, so not really dealing with the highest end horsepower, also doing that for cost purposes. So we can see here where a site ID had a record that it could join with altitude, that reference data. It populated it. If not, that's where that null comes from. So this looks pretty similar to what we got with Athena. So, you know, it's the big deal. I say by itself, to stand up a Redshift cluster and query things from S3, that's not the use case. So you're absolutely right. If that's going through your head, yes, this is not really what it's intended for. So let's go ahead and start, like, maybe looking at a bit more of a use case that involves the mixture of internal and external data. So we'll get into here, take a spin over to the console. And so I got a table called site info. And so this is going to be a table inside of the public schema within Redshift, one of the defaults. And so we go ahead and create a site ID and site name. So with that being the case, we're then going to go ahead and put one record into said table. And so we're going to say site ID 5, the site name is Charleston. If that's South Carolina or West Virginia, well, I guess that's left up to the reader. So with that being the case, let's just go ahead and double check that this is populated. I cannot type at all today. Just bear with me though. So we'll let that get queued up and get going. And so, as promised, our very simple reference data that lives internally to Redshift, site ID 5, shall be called Charleston. And so now, conceptually, we've got data in S3, and it's got a site ID, but we don't actually know the name of the site, so for any kind of report for a user, site ID 5 means very little, unless like maybe they work 20 years and they just know this stuff. But yeah, it's not a very intuitive user experience. So with that being said, let's jump back into the queries. Actually, I think I've got it in my clipboard. So let's take a look at what we're doing here in the query. So from that Spectrum schema, where we store the pressure readings, we're going to alias that P for pressure. We're going to take that and we're going to left join on internal data within the public schema of Redshift in that site info table. And we're going to call that I for info. And we're going to join on the site ID in pressure being equal to the site ID in site info. So, cool. Just as a proofs in the pudding sort of situation, go ahead and execute that. Wait for it to get queued up. Here we go. And so, oh man, we don't have any site names. Well, we only have a site name for site ID 5. So let's go ahead and get a little bit more specific with this. So here we can say P for pressure table, site underscore ID is the column name. We are using strings for IDs, again, not the most strict of data typing. Probably wouldn't fly in production, but let's just run with it for now. Cool. So now we've got sensor readings coming back, different, well, these are all produced around the same time, but nonetheless different readings. And then also now we've got the site name joined into the data. And so at this point, from the raw data, we split that into pressure, temperature. Go ahead and enrich that, send it out to S3 when query the majority of the data from S3. Then we're going to go ahead and pull that back using Redshift Spectrum here. But internally to Redshift, we also have a table with some lookup data around the site name. So pretty cool. For each kind of sensor reading, we went ahead and enriched that with one kind of data over here from S3. And then effectively, we're enriching it again from an internal table over here in Redshift. So pretty neat stuff, very powerful. What it allows you to do is to keep seldom used data at a very high scale over in S3, and then keep your regularly used data, or kind of your standard canonical data models that are normally in your enterprise data warehouse, the kind of standard data warehouse data, they can stay there. And then you can combine those in a way that doesn't require you to use your sparsely accessed data or infrequently accessed data and pull that into Redshift, which would potentially result in extremely high storage fees, as Redshift can scale out to exabyte level data. It gives you some options around how you want to store things, how, what is worthy of being brought into your data warehouse. In general, just offers you some flexibility and really a lot of power to, you could potentially, if it's a public S3 bucket, start performing queries against someone else's S3 bucket. So then you're talking about a pretty interesting scenario where you're querying your data warehouse and someone else's S3 bucket, and you're bringing all that back and you're developing some kind of report or analytics, etc. You're dealing with a pretty powerful set of use cases that are really just super prevalent. See them all the time worldwide. So pretty interesting ways to solve pretty hard problems. So with all that being said, we have jumped in here, checked out Part K data, looked at Athena, and set Elasticsearch pros. Again, the first time I'm running these slide decks, so excuse the typos. Got into Elasticsearch via curl. And we looked at the reference data in Redshift, created some stuff with Redshift Spectrum schemas / databases, and then joined that together. So next, let's go ahead and take a look at the code behind this. So this all really starts from the data stack. And we looked at this, the data science stack. We looked at this a little bit last time. So I'm not going to go through this because honestly this is getting to the point where I find it to be hard to maintain. I think I will refactor this. Didn't really have time before the meetup, but it's starting to get real repetitive. I feel like there's some better ways to do this here. But I think for the purposes of what we reviewed today, I'm talking about going back into Athena, you're talking about Glue, you're talking about standing up Redshift. Redshift Spectrum, I did not find a way to do that in the coded infrastructure. Maybe a way, I just did not have the time to do that before this started up. And then also we're talking about getting into Redshift, Elasticsearch, Athena, etc. So let's go ahead and take a look at these. So first, and we kind of looked at this, the Glue tables that have the schema. Pretty easy here with this COLUMNAR SDK. Go ahead and create a new table. Table has to go into a database, so I've got a method up here to create a database, and that gets passed in. External table, parameters, external true, Parquet compression, snappy. Then go ahead and take the list of columns, or fields as they're called here, and just create a storage descriptor column args. It's a bit of a mouthful. I will say with TypeScript, this is a little bit less verbose, but overall, love the ability to get in here into the code and basically use the code as documentation. Extremely powerful. As someone who came from a development background, I really, really appreciate that. So good stuff here. Good stuff. So then let's go ahead and take a look at Elasticsearch. And so how to create Elasticsearch. And this is pretty similar to the length of code that you're going to see with Terraform as well. Again, Terraform is going to be a touch less verbose, but for the sake of conversation, the parameters are pretty much the same as Pulumi is built on Terraform Bridge, if I'm not mistaken. So specify the domain name, specify an Elasticsearch instance type. You can scale up Elasticsearch quite a bit. And so I tried to use something pretty small, not an extra large option. I think in the relative scheme of things, this is one of the smaller options you can choose, even though it says large. Looks can be deceiving. So go ahead and set up the volume, the elastic storage, and so go ahead and get the volume set up, and this size is in gigabytes. Worth noting. So we're going to set up 100 gig storage drive for the Elasticsearch cluster. So pretty cool stuff. Also very easy. I find it easier to come in here and look at some of these arguments, for example, figure out what are all the possibilities with, like, for example, setting up an Elasticsearch cluster versus going through all of the online documentation. So to each their own, but this works really well for me. So at that point, probably worth jumping into Redshift. So we can take a look at what we did to set that up. Again, it's not a ton of code. Set up a cluster identifier, which has to be harpoon cased in terms of hyphens and underscores, so that's what that silliness is there. Go ahead, set up a cluster type, database name, master password, username, standard database stuff. So that's pretty much the gist of creating that. I will say, when instantiated via coded infrastructure, the Elasticsearch and Redshift clusters are by far the longest running. They take a pretty good chunk of time. I think to spin up this whole stack, it took something like 18 minutes, maybe. So that's why I didn't want to do that live. I didn't want to kind of keep you all hanging watching a status prompt for 18 minutes. Not a great experience. So at this point, we've looked at Glue, we've looked at Redshift, we've looked at Elasticsearch, etc. I think at this point, it's probably worth noting, going back to the diagram, that what really ties the room together, if you will, is the usage of Kinesis. And this looks like a lot, but for a enterprise level data pipeline, this is really not getting too crazy. So in order to tie all of the sources together, the analytics apps, which are enriching with either altitude or ambient temperature, and then outputting to a stream, and then getting that as like the first enriched source, if you will, all the way out to these various services, we use Kinesis extensively. And so with that being the case, driving this from the diagram, from, let's say, the pressure analytics app, let's take a look at the pressure data stream. And creating that data stream is pretty easy with the coded infrastructure tools that we have. So let's take a look at these. And so we have, let's kind of split these up a little bit. It's hard to read. So we'll create the temperature enriched stream as well as the pressure enriched stream. And to jump into the create stream method, it's really pretty easy. So specify your retention period. I believe that's in hours, if I'm not mistaken. Yeah, looks like we're in hours there. Shard count, if you want to get a level of parallelism for your stream processing, you can scale this out. Since this is a very simple demo, 1 is definitely sufficient. Then finally, tag everything, tag all the things. That'll help you find out where your money's going down the road. And just leave it at that. So back into the stack here, we do the same thing with the enriched pressure stream. So at that point, natural question would be, how do you configure the analytics app to get into this enriched stream? So that was actually a change that had to be made. The analytics apps are a little bit more of a beast. I won't get into those completely since we looked at those last time, but worth noting, in these applications, you simply specify an output. And in here, I'm specifying a Kinesis stream. And so we just give it the resource name of the stream, as well as the role that has, the privileges to produce to that stream, and then also the output format. So that was a change that was made, but we're not really making a lot of big changes from what we had previously. And so at that point, you start to look at, well, how do we start to connect these fire hoses that are going to feed our S3, our Elasticsearch, and our Redshift data sinks, if you will. That's a term that's used pretty frequently in kind of the data pipeline portion of the industry. Data stores, very explanatory. Data sync, you can think about that as a destination, if you will. So if we start to look at, well, how are we going from these streams that have the enriched data from the analytics applications, that is a Firehose configuration. So if we want to start looking at we looked at this a little bit before, but we'll just dive back in. We simply specify a source configuration. So again, we give it the Amazon resource name for the stream that we're going to consume from, as well as a role that has the ability to read from that stream. And so at that point, going from the original diagram that doesn't really fan out too much after the analytics applications into this pipeline that fans out, some might argue, an aggressive amount, you're really not talking about a whole lot more code. We talked about that a little bit prior. So the ability to start to really create these super robust data pipelines with very minimal really coding, like we're coding the infrastructure, we're not even really coding the logic, that's really more so configuration. That's something that goes pretty quickly in the grand scheme of things. So I've been a pretty big fan of putting this architecture together, the ability to change the architecture to fan it out pretty quickly. And I think to really kind of point that out is we were coming out of the analytics application that was enriching the data from an S3 bucket, that text file that we saw last time, and it's going directly to a Firehose. The change there was not to add more Firehoses to the analytics application output, but more so because you can specify one output from those analytics applications. I would have loved to just hooked up the fire hoses to the analytics application, but you get one output. So when you start to think about how to fan out data in the data pipeline, you got one output. Well, you start to think about the fire hoses, you specify an input and an output. And you can have any number of fire hoses using a Kinesis stream as the input. And so the really powerful thing there is we've got this kind of many-to-many stream processing paradigm that we start to get into. And so if we wanted to go truly many-to-many, and we certainly could, we could have had both of these analytics applications pushing out to a single stream, and then a little bit more logic about conditional filtering, stuff of that nature. But I wanted to kind of keep this diagram a little symmetric in terms of this area. And so with all that being said, I would like to thank you all for tuning in to the meetup. I don't have a ton more content. At this point, we'll go ahead and jump down to our conclusion. So what we've covered: benefits of event-driven architectures, overview of the demo architecture. We talked a little bit about the coded infrastructure using Pulumi, and we talked about the overview of the components. Then we went through a few manual steps, started looking at creating Athena, looking at Elasticsearch results, had to change the Elasticsearch privileges, etc. And so went through all that, and everything works. So I'm always pretty happy when my demo works. Anyways, enough of that. Thank you all for tuning in. Go ahead and warn you again. Elasticsearch, Redshift, extremely expensive. Go ahead and turn those off. If you have spun all of that up in Pulumi, we'll go ahead and go through the steps to nuke that stuff. Clear that out. So in our IAC folder, we'll just Pulumi destroy -y, not to prompt. And I'm going to go ahead and kill all of the things so that my company doesn't get charged an arm and a leg for running a Redshift cluster. So with that being the case, we'll get a few news and notes, a few items here. Recently the meetup made it to its 1-year anniversary. Thank you all for tuning in. Really pretty exciting. We managed to make it to over 1,000 subscribers or members of the meetup within 1 year. Really couldn't be happier with that. Thank you all. Upcoming next month, end of next month, we're going to get into IoT Core, and so Austin and I are going to pair on that. On that note, I just wanted to announce to the group that we are updating the cadence of the meetup. We've been doing twice a month, and that kind of came out of us doing a once a month trip. We were going pretty awesome places like Austin, Texas, and San Francisco, and obviously with quarantining and sheltering in place, etc., we're not able to do that. So we kind of decided to go with once a month and better content, go with quality over quantity, if you will. So just wanted to give you all a heads up there. As always, if you want to discuss, hit us up. Let us know if there's anything that you would like to learn about in the upcoming meetups. Definitely taking calls for content. We are more than interested in creating things that our community wants to see. Additionally, if you're interested in speaking, we love to have guest speakers. To be honest with you, it lightens the load, and I think more importantly for the community, it diversifies both the content itself and the content delivery. And so definitely looking for any suggestions on content or guest speaking spots are open. So like I said, hit us up. Worldwide, we do a ton of these data pipeline jobs, cloud work in general. So definitely, if you need some help, I would love to conversation started. Hit me up on LinkedIn, LinkedIn/Kevin10, easy enough to find. So with all that being said, I think it's probably Q&A time. Austin, do we have anything from the stream? Looks like we have no questions from the stream. So again, thank you all for tuning in, and I hope to hear from you in the future. Hope everyone has a good night.